Hello, I'm Michel Bierler. We will look together at a first choice model using Pandasbiogeme. We will see how to specify the model and how to estimate its parameters. The case study that we will be looking at is called Swiss Metro. Swiss Metro is a revolutionary maglev underground system that has been designed in Switzerland and which is planned to run at 500 kilometers per hour. We are interested in analyzing the demand for such a system, and to do so, we would like to estimate a transportation mode choice model where the three competing modes would be the regular train, the Swiss Metro, or the car. We will consider three variables from the dataset that has been collected in Switzerland. The first variable is the travel time for each mode of transportation. The second variable is the travel cost for each mode of transportation. And the last variable is a variable that identifies individuals who owns a yearly subscription for public transportation. Indeed, such travelers will not pay any cost to take public transportation because they own a yearly subscription. And we consider very simple utility functions where the utility of each alternative is simply a linear combination of the two variables, travel time and travel cost. We have also included alternative specific constants for all alternatives except Swiss Metro. In the specification that you see here, the parameters in red must be estimated from data. We have 4 of them: ASC train, ASC car, B time, and B cost. Now, let's see how to code such a model using the syntax of Pandasbiogeme. I have prepared a Jupyter notebook to illustrate the various steps of the model specification and the estimation of the parameters. The first thing to do is to import 3 packages. Panda, which is the Python package designed for data management and analysis. And here we will use the shortcut PD to refer to Panda. Then biogeme.database, which is the biogeme package that is designed for the database preparation. And we will use the shortcut DB. And then biogeme.biogeme as such. And we will use the shortcut bio to refer to it. Now the first thing to do is to prepare the data. We will read the data from a data file called swissmetro.dat that can be accessed from the internet. And we use the Panda function called read table. It reads the data file and stores the results in a Panda data frame. Actually, we can print this Panda data frame. As you can see, you have as many columns as there are variables in the data file, and as many lines as there are observations. We have 10,728 rows and 28 columns. Another way to look at the data is by using the function describe, that for each column, so for each variable in this data frame, provides various statistics: the count, the mean, the standard deviation, and so on. Next, we create an instance of a biogeme database by providing a name and the Panda data frame as arguments. During the construction of this instance, biogeme creates a file called headers.py that actually defines all the column names as variables. In order to be able to use these variables, we need to import this file, and we use this statement from headers import star. Afterwards, we need to remove some observations that we don't want for the model estimation. We first print the sample size before, and as we saw before, it's 10,728. And then we define an exclude variable. And the idea is that this variable should be 1 if the observation must be excluded, and 0 otherwise. So here, this condition says that we will exclude all observations such that the purpose is not 1 and the purpose is not 3, or the choice is 0. Note that the multiplication is associated with a logical AND, and the addition is associated with a logical OR. And because we need to check if this variable is 0 or 1, we actually check if it is greater than 0 or not. And then we provide this exclude variable to the remove function of the database. If we print the sample size afterwards, we realize that there are 6,768 observations left in the sample. We move now to the model specification. First, we list the parameters that will be estimated. So we define a Python variables for each of them, and it is equal to the function beta that takes 5 arguments. The first argument is the name of the parameter that will be used by Biogeme. It is highly advised to use the exact same name in this argument as for the Python variable which is associated with the parameter. The second argument is the starting value of the parameter for the estimation. Most of the time, the value of 0 is appropriate. The next two arguments are the lower and upper bounds on the value of the parameters. If you do not want to put any bound, like in this example, you use noun as the value for the bound. And the last argument can take two values, 0 or 1. The value of 0 means please estimate the value of the parameter. And the value of 1 means keep this parameter fixed during the estimation to the value which is given as an initial value. So in this case, we have actually used this last argument to normalize the alternative specific constants for Swiss Metro to the value 0. Because we have put 1 there at the last argument, this alternative specific constant will not be estimated, it will be maintained to 0. The other 4 parameters have a value of 0 for the last argument, meaning that they will be estimated. Next, we will define new variables. There are two ways to do this in Pandasbiogeme. The first way is by using Python variables. So for example, here we define the cost of Swiss Metro, SM cost, as SMCO, which is the name of the variable from the database, multiplied by GA equals 0. It means that the value of the cost will be equal to 0 if the person owns a yearly subscription, so when GA is not equal to 0. And if it is equal to 0, then the expression GA equals 0 is equal to 1, and therefore the cost of the Swiss Metro will be exactly the cost which is in the data frame. And we do the same for train cost. This way of defining new variables is very easy and very simple. However, it has one disadvantage. The calculation of these operators, the multiplication here and the logical operator, will be done again and again each time the variable SM cost is used later on in the model. If you have a very complicated model and a big database, it generates a lot of calculation for each iteration of the estimation algorithm. So that's why there is a second method to define new variables. And basically the idea is to add a new column in the data frame that can be accessed directly afterwards within the model. And this is what is done for the other variables using the function define variable. This function takes 3 arguments. The first one is the name of the new variable that must be defined. Again, we strongly advise to use the exact same name as the Python variable where it will be stored. The second one is the formula. And the third one is the database, the Biogeme database that we have created. After having defined the parameters and the variables, we can now specify the utility functions. and it is done in a relatively straightforward way. So we write the utility function for train, and we call it V1. For Swiss Metro, we call it V2, and for car, we call it V3. The next thing to do is to associate these formulas with the numbering of the alternatives. To do that, we use a dictionary, a Python dictionary. The keys of this dictionary are the numbers, 1, 2, 3, and then we associate each utility with the corresponding number. We do the same for the availability conditions using also a dictionary. We define for each alternative, 1, 2, and 3, the availability condition. In this case, they have been defined above using the variables that we have created. And now we need to write the formula for the contribution of the log likelihood function for each observation. In this case, it's the logarithm of a logit model, and we use the function biologlogit that takes 3 arguments. The first one is the dictionary that contains the utility functions associated with the numbers. The second one is the dictionary containing the availability conditions. And the third one is the name of the formula that will calculate the choice associated with each observation. In this case, it's simply the name of the variable choice which appears in the data frame. We now have all the ingredients that are necessary to estimate the model, so we create an instance of Biogeme by invoking the constructor, which is Biogeme in capital letters. It takes 2 arguments. The first one is the database object that we have defined above, and the second one is this formula that describes the contribution of the log likelihood function of each observation. We also provide a name to the model that we have created. Here we call it 01 logit because it's the first model that we define, and it's a logit model. This name will be used to create output files containing the results. And now we can estimate the parameters. We simply call the function estimate of the Biogeme object, and the results will be stored in the variable results. For some installations of Python, there may be some warnings like the one that you see here on the screen. This warning can be safely ignored, and it's very likely that it will not appear on your own distribution of Python. Now we can read the results. So the object results contain all the results from the estimation, and there are many ways to access to them. Here we will first get the estimated parameters, and we store it in a variable called Panda results because it's actually a Panda data frame that is printed here. If we print the results themselves, you have a lot of information, including the general statistics and information about the parameter estimates and the correlation of the parameters. But this format is not very nice to look at, and actually Biogeme is also creating an HTML file. The name is 01logit.html that contains all these results in a nicer format. The HTML file contains the estimation results. It provides first various general statistics, the number of estimated parameters, the sample size, the number of excluded observations, the value of the log likelihood function calculated at the initial values of the parameters, the value of the log likelihood function at the end of the estimation, the likelihood ratio test comparing these 2 models, so the final one and the init one, and the rho square and rho square bar also for the init model. It calculates as well the Akaike and the Bayesian information criteria, provides the norm of the gradient of the log likelihood function at the final value of the parameters. It reports the diagnostic generated by the optimization algorithm. It reports the number of times the database has been read and the number of iterations. And then it provides information about the data processing time and the time to solve the optimization problem. Finally, The number of threads which have been used for the estimation is also provided. The next table provides for each parameter the estimated value, the standard error calculated from the Rao-Kramer bound, the corresponding t-test, and the corresponding p-value. These three quantities are also reported using the robust variance-covariance matrix of the estimate. The last table reports for each pair of coefficients the covariance, correlation, t-test, and p-value using the Rao-Kramer bound, and the same quantities using the robust variance-covariance matrix. Finally, the smallest eigenvalue and the smallest singular value of the log likelihood function are reported. If these values are close to 0, this is a sign of potential misspecification of the model or lack of variability of the data.